Hi, welcome back. So today we're going to continue to look at the normal distribution. The other day, just kind of a recap, we looked at how the standard normal distribution was set up, and we used the normal distribution table to learn how to take a Z-score and find probabilities on that curve. Today we're going to continue to look at that, but we're going to look at how this actually applies to real-world situations. It's very common that data that we collect fits a normal distribution. So if we can take this concept and apply it, it fits into several different occurrences that we deal with on a regular basis. So standard normal distribution, like I said previously, also can be used to solve a variety of problems. Whenever we do this, though, we're going to have to make a transformation to the standard normal variable. So that would be to make a Z-score for our value that we're working with. Now, we mentioned this earlier as well, and we've covered it in earlier units. The Z-score formula is equal to X, which is whatever our value of concern is, minus mu, which is the mean of the population, divided by the standard deviation sigma. So, and that is lowercase sigma, not uppercase like we've talked about in other circumstances. So, we have X minus the mean divided by the standard deviation, and that gives us our value for Z. Now, in our previous lesson, I gave you the values for Z to work with. Here, we're going to actually have to work out what this value is going to be. So what is a Z-score? And let's kind of get an idea of what it actually means when we're working with it. First off, the formula again is X minus mu divided by the standard deviation. What this is a measure of how many standard deviations a value is away from the mean. So knowing that kind of tells us how far out away from the middle of our normal curve this value is going to be. So if we have a negative Z-score, that would indicate that our value is actually below the mean. So if I have a value that has a negative Z-score, that means that whatever it is scored or came in underneath the average. If the Z-score is positive, that would mean that it comes above the mean. So for example, if we had we took a test and our test score had a Z of negative 1.27, that would indicate to us that whatever score that is, it was 1.27 standard deviations less than the mean. So it's a little bit below average. Actually, in this case, that would be quite a bit below average. Negative 1.27 would be more than a whole standard deviation. So if it was positive, say it was positive 0.85, that would mean that you scored 0.85 standard deviations above the mean. And whatever that standard deviation is would determine how far that was. But that's just kind of a reference for what we're talking about when we say Z-score. So let's take all this and let's get into an example here and look at how this works out with our problems. Survey found that women spend an average of $146.21 on beauty products during the summer months. The standard deviation of the data is $29.44. So we want to find the percentage of women who spend less than $160 and assume this variable is normally distributed. So, we might be doing some things. We might be marketing cosmetics, some kind of summer line of cosmetics we were coming out with. And if we were wanting to know that, we might want to have an idea of how much spending was going on. So we may want to know how many women or what percent of women are going to spend less than $160 on beauty products during the summer. And these numbers are just kind of made up for this problem, just so you know. It's not real. It might be, but from my information, it's not. At any rate, we're looking at $160 here. Our mean, which is in the middle of everything, is $146.21. $160, of course, is a little bit more than that. So we would expect this to have a positive z-score because it's a little bit above the mean. Now, what we want to know, though, is the percent of data that comes below this $160. And hopefully you'll remember from our lesson that what we do when we're looking at something below it. And we'll talk about that more in a second. But what we're going to do first is we're going to find the z-score for $160. So we'll convert that to a standard z, and that is going to be 160, which is our value for x, minus the mean, $146.21. And we're going to divide that by our standard deviation, 2944. Now, you got to be careful. If you punch that in the calculator all at once, you're going to want to put parentheses around this, because if you don't, it's going to follow the order of operations and not get you the right value. So 160 minus 146 over 0.21 is 1379. And when we divide that out, we find that we have a z-score of 0.47. So we said that we were a little bit above that mean, and in this case, we're 0.47 standard deviations above the mean of 146.21. So that is our z-score. Now, you'll recall at this point that what we do now is we go to our table, and I'm going to just kind of go to the table and show you. We're going to look at 0.47 on our normal distribution table. And the way we do that is we would go to 0.4, positive 0.4, which is right here. And we would move all the way over to 0.07, excuse me. And our value would be 0.6808. So that's going to come into play here, and you can see after we've worked that out, we go to the table and find the percent of data that is to the left of 0.47. Now, you'll recall that if we were looking at data to the left, we're just going to take the value that we get from the table and apply that to our answer. That would be our answer. So what we're saying here is that this whole area represents 68.08% of all the population. In other words, 68% roughly of women spent less than $160 on beauty products during the summer, according to this problem. Okay, let's look at another example. Each month, an American household generates an average of 28 pounds of newspaper for garbage or recycling. Assume the standard deviation is 2 pounds. If a household is selected at random, find the probability of generating more than 30.2 pounds per month. And I did leave out in there that this will consider that this is a normally distributed population. So if we want to first off kind of sketch or draw out our situation, we're looking at a family coming in at more than 30.2 pounds per month. So what that would look like is we have a mean, excuse me, let me pull this up. See if I can get there. Okay, so we have a mean of 30.2, or that wasn't what it was it? 28. So we have a mean of 28, and that means that this middle right here is roughly 28, and 30.2, excuse me, 30.2 of course is going to be above that somewhere, and I'm just kind of eyeballing it. And we want to see what is the probability that we are going to have, or what percent of households are going to be above 30.2. So we're looking in this area here. So what we're going to do is we're going to look up our z-score. We're going to find our z-score first. And the z-score is going to be 30.2 minus 28 divided by 2. So that's 2.2 over 2. And that's going to be a z-score of 1.1. So we will go and we will look that out in the table. Again, I'm trying to jump between screens here. We have a z-score of 1.1. So 1.10. And that would be right here, 0.8643. Now what that represents, and if you ever forget, you can kind of look up here at the top, that is the area that's to the left of our cutoff point. And you'll see that in your drawing up there on top of the table. So that 1.1 z-score, and what was it again? I just forgot what the 0.8643. So that is going to be what is in this area here, 0.8643. Well, that's not what we're interested in. We are interested in this area over here. So what is that? That is going to be 1 minus 0.8643. You'll remember our rule said yesterday when we talked about this, we said that when the value of concern was to the right, or greater than our cutoff point, we wanted to subtract our value from the table from 1. And this is what we're doing here. So that would be where we get our answer. So what we're going to end up with is 0.1357. So this 0.1357 is basically saying that 13.57% of households are going to generate more than 30.2 pounds per month, according to this problem. Okay, so we've looked at a situation to the left and a situation to the right. Say we were looking at the same scenario now, where we're dealing with the amount of recycled paper or newspaper for garbage and recycling. The mean was 28, and now we want to look at a family generating between 27 and 31. Now we're looking at the same situation, but we have two values that we're trying to come between. So we're going to do what we did before. We're going to find z-scores for both variables. The z-score for 27 would be 27 minus 28 divided by 2, and that's going to be negative 0.5. Okay, and our second z-score for 31 would be 31 minus 28 divided by 2. That's going to be 3 over 2, which is 1.5. So we're going to take those values and we're going to then look the values up in the table for 1.5 and negative 0.5. So if we look up 1.5 in the table, or excuse me, if we look up negative 0.5 in the table, we're going to get 0.3085. And if we look up 1.5 in the table, we are going to get 0.9332. Now remember, those are percentages. You're always going to look up those values first, and then you're going to subtract them. So 0.9332 minus 0.3085 would give us that the area between these 2 points is going to be representing 62.47% or 0.6247. So that is our solution to this problem. Again, you have the situation where if we're looking at data to the left of a cutoff point, we're going to take the value from the table and just use it. If we're looking at data to the right of a certain value, then we are going to look at z-score up and subtract our answer from 1. If we're looking between two values, we're going to get z-scores for both values. We're going to look them both up in the table, and then we're going to subtract the percentages that we get for each one, and that will give us the area between. Okay, now another situation happens that's a little more complicated when we have to work backwards. For instance, we might know the percent that we want to fall into, and then we need to know what the cutoff point for that percentage would be. Here's an example. Well, we'll look at an example in a second here. To qualify for the police academy, a candidate must score in the top 10% on the general test. So we say that whoever applied, out of all the people that applied for the police academy, we're going to take the top 10%. The test has a mean of 200 and a standard deviation of 20. Well, if I'm taking this test, I know that I got to be in the top 10%, but what does that mean to me? I need to kind of have an idea of what exactly that means to score in the top 10%. What is my cutoff point? What score do I have to get into that top area of the top 10%? Kind of important for us. So we kind of take that information and we can go to a distribution. Excuse me. Let's see if I can get. Okay, so if we're going to take this and go to a distribution, again, we know that our mean is 200, so that would be kind of right here in the middle. And we know that we want to get into this top 10% area. So we're going to try to get over here. We know that this is representing 10%, which would be 0.1000. But we don't know what score that is going to take for us to get there. So what we're trying to figure out is how this is going to work with going backwards. So first off, we need to recall that we're going to work, when we work with this table of values, the table of values is always going to give us what lies to the left of our value. So we're looking over here at this section. So what we need to kind of know is, if we're looking at the top 10%, we need to kind of understand that below the top 10%, you would have 90% over here. Now, the reason why we want to know that is because when I go to my table over here, the table is always given me, let me clear a couple of things out. The table has always given me the values of the percent to the left of our cutoff point. So as you can see kind of in this drawing, we're always looking at things to the left of our cutoff point. So what we're going to do is, we know that our percent over here is going to be 90%. So what we're going to do is we're going to kind of look through all of these percentage values in this table and try and find the closest thing to 90% that we can. Now, in most cases, you're not going to hit exactly on the number, which is fine, because a lot of this is just a rough estimate, but we're going to get it very close. So you can see these are in numerical order, and the best thing that I can find, the closest thing that I can find to 90%, you can kind of see we're around in here, would be 0.8997. Now, you got 89.8% above, that's 90.15%, which is still pretty close, but the closest one is just slightly below 90% at 0.8997. So we know that that is the percent that we're going for here, or the closest we can get to it. So what we're going to need to do is identify what Z value that is. So that's 1.28 would be the Z for that problem. So we're going to say that our Z is 1.28. Hopefully you don't scribble on your table like that, but we know that whatever we're dealing with is Z is 1.28. And after that, it becomes an algebra problem. We're going to just go back to our problem, and we can set an equation up. And again, if 10% is going to be to the right, we know that we have 90% below the score, and we're using the table to get that 90%. So find the one that's the closest to 90%. It's going to be 1.28 for our Z value. So like I said, we just did all that. Now we're going to set up an equation based on this Z equals X minus mu divided by the standard deviation. What we're trying to find is X. So we're going to plug everything else in. We know the mean is 200. We know the standard deviation is 20. And we know that our z is 1.28, or very, very close to it. So we're going to just kind of take this and solve the equation using algebra. We'd multiply 20 over and then add 200. We multiply 20, we get 25.6. And that leaves x minus 200 on the right. And then we add 200 and we get 225.6. Well, what that means is that the score to get to that top 10%, the cutoff point would be 225.6. Now, if it's like most tests, you're not going to hit a 0.6 as a score. So we would say that we have to get a little bit above that to get into that top 10%, because if we get below, we're not in there yet. So we would round that up to a score of 226. So basically, if I want to get in the top 10% on whatever this test is, I'm going to have to score a 226 or higher. And that might be something we would want to know going into this test. Okay, so we're going to look at a couple of more practice problems here. Let me pull that up on my Cami, and we will go with it there. So SAT scores are normally distributed with a mean of 500 and a standard deviation of 100. And we want to find the percent of students that score above 620. So above 620 would be very important for us to understand here. We're looking at a distribution, and you don't have to draw it perfectly, but we know our middle would have 500. Now 620 would come somewhere on that scale, but we should know that 620 is above 500. How far above, we don't know right now, but we know it is above. And we want to find the percent above. So we are looking at what percent is going to come above 620. So we will work out a z-score for this problem. So what we're going to say is that z would be equal to, we'll say what? We have 620, which is our score, minus the mean of 500. And we're going to divide that by the standard deviation of 100. Now, you're going to find that that's what 120 divided by 100. And that is going to give us a z-score of 1.20. So we're going to look up 1.20 in our table, and then we'll go from there. Now let me clear some of this stuff out. Yeah, that's why you don't mark all over your table right there. So we go to 1.20 on our table, and that's 1.20. So that would come right down here. And that would be 0.8849. And we're going to take that 0.8849 and understand what that represents. That represents the area to the left, 0.8849. Now, that's not what we want. We want the area that's over here to the right. So what we're going to do is we're going to say 1 minus 0.8849. And again, you can just realize this because we're talking about coming in above something or greater than something. And 1 minus 0.8849 is going to equal 0.1151. So basically, given this information, and that is actually pretty close to the truth. It varies a little bit year to year, but the mean is usually around 500 with a standard deviation of 100. Basically 11.5% of people are going to score, or 11.5% of students are going to score above 620 on the math section of the SAT. All right, continuing along, now we're in a situation where we want to know what percent or what score is it going to take to beat out 30% of the students taking it. So let's look at our curve again. So we've got our distribution curve. And, you know, again, I'm not an artist and it doesn't have to be perfect, but just kind of get a relationship but here by sketching. We know the mean is 500. 30% we want to beat out. So if we got 30% below, that would be down here somewhere. And we know that there would be an area back here to the left of 30%, 0.300. So we want to know what score it's going to take to beat out that percentage. So we're going to go to our table. Since this is to the left, we're good to go. So we'll go to our table and we are going to find the closest thing to 30% that we can. Now you're going through all these numbers. Now a common mistake that a lot of people make is they go and they look here and say, oh, that's almost 30%. Well, that's actually 3%. So make sure you're paying attention to your decimal places. We want the closest we can get to 0.300. So that would be down here. We're going, and I should know this, but the numbers are in order, and the closest we can get, it looks like, is 0.3015. Okay. And, you know, you can see this is close to 30%. It's a little bit, it's 50 points above. This is close to 30% as well. It's 19 points off. 30.15 obviously is going, or 0.3015 is going to be 15 points off. Now we want to know what Z-score this is. That's negative 0.52. So we're going to take that negative 0.52 back to our problem and work with that. So we know Z is negative 0.52. I don't make fives very good on this screen. Okay, so we're going to take our equation then and work with it. We have a mean of 500, a standard deviation of 100, and we are trying to find X. So let's work with that. Let me see if I can get this set up a little better. Let's see. Z is going to be equal to, this would be X, which we don't know, the score, minus the mean of 500, and that would be divided by the standard deviation of 100. And I should have had Z there because I know what Z is. My Z is negative 0.52. And now we're just going to solve this equation. Well, 100 times, we would start off by multiplying 100 to both sides. That's to cancel that out. Excuse me. So we'll multiply 100 over here, and we'll multiply 100 over here. So that's going to give me negative 52 when I multiply that. And that would be equal to X minus 500. Well, your next step would be to add 500. And that would mean that our answer would be X is equal to 448. So a score of 448 would beat out 30% of the people taking this math test. So, you know, there's an example of how we work backwards with this. Now, working backwards is a little more complicated, but again, we're working with the concept that our table is always going to give us the percentage to the left, and we can work with that and find our Z from there. Okay, well, that was a good lesson for us. Hopefully you can get some of these concepts and continue with them in your exercises. If you're having any problems, please feel free to reach out and contact me in class or through email. Have a good day.